Hello community! Today we have some brand new insights into AI agents. We have here research from Princeton University, July 2nd, 2024, AI agents that matter. But hey, a little warning, if you want to live in your AI bubble, if you want to continue to be in your bubble, do not watch this video. Go for a walk and come back in about 20 minutes time. Now, this research is nice because it focuses here on realistic performance of AI agents, or as they call it now, compound AI system. And they say here, an AI agent evaluation differs significantly from an LLM for a large model evaluation in fundamental ways. So don't mix it up, because agents, they don't have a single correct answers. An agent can cost much more than a single LLM call. And for example, they give us the SWA agent, even capped each run on the agent after $4, but this translates already to hundreds of thousands of LLM tokens. So you see, the complexity that is running behind the scene can be quite impressive. So they say, why we did this study? We want here, our overarching goal is to stimulate the development of AI agents that are useful in the real world, and not just accurate on some synthetic benchmarks. And since we are here talking about Princeton, we have here an absolute scientific way to approach this. So our first question is, what is an AI agent? What constitutes an agent in the context here of LLM-based systems? And Princeton says, I'm not going to give you the 28th definition of what is an AI agent, but I go here with this agentic system. So what we have, Princeton tells us, hey, there are three factors: the environment, the more complex the environment, the more complex goal we have, the more agentic our system is. User interface: if you can talk to your AI agent in a natural language and the AI acts autonomously on user's behalf, this is also a good sign that it is more agentic. And then we have the system design. If AI systems here, the agent systems, use different patterns such as a tool use or as a planning, then they're also more agentic. And you say, what do you mean with agentic? Well, it's a fallback solution, you know. If you have two people saying, hey, this is an agent, this is not an agent, you know, there's a simple solution. You say it is agentic, and agentic has here a spectrum from 0% to 100%. So everybody will find here itself within the terms of agentic. Either your system is 0% agentic or 100%, but it is agentic. Following here, Andrew. Thanks, Andrew. But of course, we are back here to some pure university research, so we need much more stringent definitions. So here we go. They found that you can increase the accuracy by simple measures. And they said calling language model repeatedly and taking a majority vote can lead to non-trivial increases in the accuracy of the systems. And they give you the example of AlphaCode, where you can increase here from close to 0% accuracy with a zero-shot base to over 15% accuracy with 1,000 retries and over 30% with 1,000,000 retries. And they say, hey, there's seemingly no limit to the amount of inference compute that can increase the accuracy of the system simply by increasing the budget. Oh, great. Well, next step, we need to know a little bit about the Pareto efficiency and a state of resource allocation where it is impossible to make any one individual better off without making at least one individual worse off. For my green grasshoppers, great. And they now analyzed three particular AI agents where they shared the code publicly, so we can have a look inside those agents and evaluate those agents. Princeton did it for us. And here we have our three agents. Now, let me introduce them to you. Language Agent Tree Search, or as they call it, LATS, unifies reasoning, acting, and planning in language model. Beautiful. June 2024. Have a look at the GitHub. This is a real interesting publication here for an evaluation agent. Then we also go debug like a human LLM model debugger via verifying the runtime execution step by step. This is called LDB for a debugger. And then the third one is reflection by MIT and Princeton University, end of October 2023. And here we have language agent with verbal reinforcement learning. So instead of updating here the weight tensors, this is done through linguistic feedback. Very interesting. Have a look at you yourself. So those are 3 agents. If you're familiar or not, never mind, because we show you the result. Now, second most important step is they do not focus only on one function in the evaluation, but now they integrate here the cost and the time requirements for running those agents. And they have 4 configurations for running those agents. A pure vanilla configuration, GPT 3.5 and GPT 4. A retry configuration, where they invoke a model with a temperature set to 0 5 times. And retrying makes sense because LLMs aren't deterministic even at a temperature of 0, which might be news for some of you. The configuration warming, the same as the retry, but they increase here the temperature of the underlying model with each run from 0 to 0.5. And the configuration escalation, very simple. They start with the cheapest model, Llama 3 8B, and escalate to the most expensive model, GPT-4. So here we go. What are the results? Please note we have here the accuracy on the y-axis and the cost on the x-axis. And here we go. And now you see here suddenly the Pareto frontier. And this frontier here helps us to identify the most efficient agents that provide the best balance between 2 functions. And here it is, cost and accuracy. So you see, in our scenario where we analyze 3 different modes, the zero-shot models here in the green square, then a baseline agent and a complex agent, you see GPT 3.5 here with green or GPT-4. They are really close to the Pareto frontier as a zero-shot model. But if we enter now the agent model, you see here that even a baseline agent model like escalation has a nice accuracy of 85% and the costs are minimal, close to 0. And then you can go up here to warming, and we have here GPT-4 used for both the code and the debugger. So excellent, close to 95% performance, real beautiful cost structure. But of course, if you look here deeper, you have to be aware that the underlying model for code and debugging, of course, has also a cost influence. So if you go with a cheaper GPT 3.5 or you go with the more expensive GPT 4, yes, your accuracy increases for the same agent, but also the cost. And look here, the cost is here at about, I don't know, let's say 10, but this cost is here at close to $135. So, okay. But you might say, how is it now? How is the sensitivity now to a baseline agent, to a complex agent? And here we have the data. You see, close to the Pareto frontier, we have here a baseline agent retry where we have GPT-4 both for the code and the debugger. And yes, above 90%, nice, and not at all expensive. And at the same level of accuracy, you find here a very complex agent, or LDB, or a debugger, which uses here the reflection configuration and GPT-4 as the LLM. And you see, well, it is almost on the same level of accuracy, but this complex agent, LDB, is much more expensive, much more to the right on the x-axis. And we have the same here if we have here the warming, a baseline agent with GPT-4, beautiful, close to 95%, and at the same accuracy level, close to 95%, but more expensive, we have the complex agent. So you might say, why should I buy here or pay for a more costly complex agent? Well, welcome. So Princeton tells us, there's a lack of evidence that System 2 approaches are responsible for the performance gains. Since papers proposing a new agent have not adequately tested the simple baseline of those agents, it has led to the widespread belief in the community that complex ideas like planning, reflection, and debugging are responsible for those accuracy gains. But Princeton says, hey, based on our findings, the question of whether those debugging, reflection, and other such System 2 approaches are useful for code generation remains an open question. And this open question is in line with other recent findings. Let me break your idea of the perfect AI agent world even more and let me show you the recent findings. You have here, end of May 2024, Arizona State University, on the brittle foundations of React prompting for agentic LLMs. And they say, yeah, this React-based prompting, and there's so much hype about it, But we in the paper, we examine here this React-based prompting in improving here the agentic LLMs for sequential decision making. And they did a systematic variation of the input prompt here, and beautiful. And they found that instead, the performance of the LLM is driven by the similarity between the input examples, tasks, and the queries, implicitly forcing the prompt designers to provide instance-specific examples, which significantly increase the cognitive burden on the human. And the investigations show that the perceived reasoning abilities of LLMs stem from the exemplar query similarity, rather than any inherent reasoning abilities. So this is kind of a devastating finding. And maybe you have not seen this publication. Give you another one, Google DeepMind. LLM models cannot self-correct reasoning yet. You say, wow. So, that there's the belief that there's a self-correction in the LLMs. This is proposed as a remedy here to problems that we have. And they say central to our investigation is the notion of intrinsic self-correction, whereby an LLM attempts to correct its initial responses based solely on the inherent capabilities. And they say our research indicates that LLMs struggle to self-correct their responses. So another detailed studies that show us what we think or what we were told, that we have a self-correct reasoning in our LLMs. No, we do not have it if you have a detailed analysis and you inspect it here much closer than the normal literature. Coming back now to our topics, now that we are disillusioned of the beautiful world of AI agents, they say now, hey, listen, accuracy alone as one factor alone in the evaluation cannot identify the progress because it can be improved by scientifically meaningless methods such as simple retrying. And they say, but you know what? Jointly optimizing now the cost and the accuracy, so we have two functions to optimize, can yield better AI agent designs. Isn't that nice? And they have a new example, and it's a hot pot question and answer. Never mind, we will use DSPy. And again, we have 5 agent architecture that we will try and test out. Well, Princeton did it. At first, we have the uncompiled configuration. Then we have formatting instruction only. Then it becomes interesting. FewShot uses here DSPy, and random search uses also here the DSPy random search optimizer. But then comes the absolute new part, the joint optimization. And they use here a specific open source system, Optuna, to find here the Pareto optimal agent design. And they analyze here multiple parameters: the temperature of the model within the agent, the number of the few-shot examples, the selection of specific examples, and whether to add formatting instruction, yes or not. Now, if you do not know Optuna, it's an open source hyperparameter optimization framework to automate hyperparameter search functionalities. You have code examples. Beautiful. It is framework agnostic. If you want, choose this or any other analyze system of your liking. Let's go to the result. Again, we have the accuracy on the y-axis and the cost on the x-axis. So let's just jump right into it and let's see here the DSPy values here and the joint optimization. Joint optimization is a green dot. Great. So let's have a look at this. So we have here Llama 370B. The joint optimization is here our green dot here. At this level of accuracy and almost at the same level of accuracy, we have the Llama 370B few shot and random search, so our DSPy optimized system. And you see for, 1 or 2 percentage point better accuracy, you have to pay significant more money for this. Or let's have a look here at GPT 3.5. Again, here our green dot for the joint optimization, this accuracy. And you see even below accuracy of GPT 3.5 joint optimization, you have the random search and a few shot with DSPy, which has even less accuracy and is much more expensive. So this is now interesting, and the authors say, joint optimization allows for an efficient agent design. And it comes at a small fixed cost for optimizing the design, but this is insignificant if the agent is used hundreds or thousands of times. So if you factor in the cost, now the performance looks completely different of those systems, because the joint optimization beats here at the same performance in price the other DSPy systems. If you want to know more about joint optimization, how it works, how this is here done for the Pareto optimal agent design, of which temperatures and what are the pipelines exactly, here are some of the numeric values for you. And for my green grasshoppers, the differences between DSPy, and I have a lot of videos on DSPy, and joint optimization, very simple. DSPy is primarily focused on improving the prompt engineering for LLMs to enhance the application effectiveness. On the other side, joint optimization is a broader concept used in AI agent design to balance here multiple factors like cost and accuracy to develop more rounded solution. And for the absolute expert, I have a new video where I show you that Stanford University, which about a year ago developed DSPy, now Stanford has published a new, more advanced system, and it is called TextGrad. Have a look at my video playlist if you want to see the details of this new methodology. Princeton also found that there's another topic here with AI agentic evaluation structures. Because, there are two different groups with two different benchmarking needs. At first, you have the scientific model evaluation with no money involved at all, where you, as a researcher, you can scale and you can find your parameter where you want to show here your Pareto curve that are non-standardized, and that you choose whatever parameter your model is best at. And then we have the downstream evaluation. This is an engineering question, and here this is now a procurement decision, which model you're gonna buy, which agent you're gonna integrate into your system. So here costs are paramount. And they say, sometimes we have evaluation on purely scientific questions that are not at all taking care about what it costs. And if you do here the downstream evaluation, here costs are paramount. And be aware that you have two different evaluation schemas. And then Princeton found, this AI agent benchmarks that and maybe you use, they allow for shortcuts. And you might be saying, what? Unbelievable shortcuts? Yeah, one, for example, is overfitting. And this is a prominent type of a shortcut and a serious problem for agent benchmarks, or to be more precise, agentic benchmarks, since you can simply have here that you directly program here the solution into the agent. And about fairness. And Princeton proposes here a core principle that the more general the intended agent use is, the more the held out dataset should differ from the training dataset. So simple solution, but nobody seems to be interested to do this if they want to sell their agent. So Princeton said, hey, we analyzed 17 agent benchmark on 4 levels of generality, and they had a deep dive. And they said, well, in principle, a lookup table can achieve 100% accuracy on many agent benchmarks. So yes, you can cheat your way into 100% accuracy. And be aware what different agent benchmarks do. And here in the annex of the research publication, you find here all the different benchmarks in the different domain, and they analyze this in detail. A real interesting insight into AI agentic benchmarks. Plus, they didn't stop here, and Princeton goes on and says, we do have inadequate benchmark standardization, and this leads to not reproducible agent evaluations. And you say, okay, I give up. So I see this is a complete mess. Everybody is just depicting what they think is the best cherry of their models. And as a consequence, the results across the evaluation studies are not comparable, potentially overestimating your own agent capabilities. The increased resource demands hinder now an efficient research progression. This means those AI agent evaluations, they are so expensive that hardly any university can afford to have some independent evaluation data. And therefore, the downstream, the engineers, the developers who integrate this into real-world systems, they make decisions based on misleading performance data, which is not so great. So here we are, short summary. Princeton University, July 2nd, 2024, AI agent and matter. Complex agents often do not perform better than simpler, less costly agents, which is a real shock. A significant number of agent evaluations suffer from a lack of standardization, are not reproducible, leading here to particular inflated performance metrics, and many benchmarks allow for some very specific overfitting. Great. And if you have then those benchmarks and those agents in real-world application, they perform poorly. So you might say, hey, great. But it takes Princeton universities to have this independent research. And I think it's great that the university look at this. They just not only look at this, but they also see what are the problems, what are the shortcomings, and they now propose a new framework for the evaluation of AI agents or agentic systems. And these points. So first is a cost control evaluation. Not just one function, but multi-dimensional evaluation, including the real costs. Second, show us the Pareto curve for trade-off visualization. We want to know how good are our agent and our LLMs really on the perfect balance of multi-function evaluations. Third, careful. There's a difference between a model evaluation on pure scientific grounds, where the researcher find here their parameters to show you how great the model is, and a real downstream evaluation if you are an engineer and you have to integrate it in your company system. Plus, to combat the variability in evaluation practice, which lead to non-comparable results, we need a new standardization that is reproducible for everybody. Then, of course, to prevent here the development of AI agents that perform well only on syntactic benchmark, like, as Princeton tells us here, exploiting loopholes or specific dataset quirks, but perform poorly in real-world scenario, please avoid overfitting. We want to have the real data, not the optimized data in your evaluation. And we need to go beyond traditional metrics like a single function, like only focus on accuracy. And we need to incorporate factors such as robustness, adaptability to real-world changes, and the economic efficiency. So a multi-function, multi-dimensional optimization problems that can easily be solved, as Princeton shows us. In conclusion now, they say, hey, AI agent benchmarking is new and best practices have not yet been established. And they say, our thesis is that AI agents are sufficiently different from large language model and that benchmarking practices need to be rethought. And I absolutely sign this. Yes, absolutely. We need better evaluation systems for AI agents that are standardized, reproducible, and university can afford to run those. And the last personal note here at the end of this video, you will see now more and more here, like this publication, warning about an AI bubble. And well, if we have AI agent benchmark that promise us the blue in the sky and deliver almost nothing of what they promised, yes, we are in the danger of generating our own bubble where we will be disappointed because a lot of people are not absolutely aware of the shortcomings of our current evaluation procedures, and therefore it is so great that Princeton University published this independent report, and I kind of like this critical review of whatever the industry or whatever the developer are presenting themselves to the community. But of course, if you think about our global AI provider, there's another topic, and it is from here that they say Sequoia Capital say also they are sounding an alarm, and they say, hey, that the industry, the AI industry, needs to generate $600 billion in annual revenue to sustain itself. And we are talking about real revenue and not some hypothetical valuations of startup companies. No, you have in the industry to generate $600 billion in annual revenue. And we are not there at all. So be prepared that our global beloved friends, our AI providers, might increase the AI prices significantly in the second half of 2024 and entering 2025 because they are faced with a real problem. They don't have the revenues. Plus, of course, you have the report by Goldman Sachs, as I already reported, that also caused some doubts based on financial performance on the generative AI. So you see, it is also up to us as a community to be transparent, not to promise something in AI benchmark or new AGENTIC system that we all know are pure marketing. We have to be realistic. We have to present realistic expectation because all the companies that try to implement those AI solutions, if they are all disappointed, if they all do not deliver the value for the companies, well, there is a theoretical danger that we are really in an AI bubble. I hope this video was informative. I hope maybe you discovered some new insights, and it would be great to see you in my next video.